Hello everyone, I'm Austin Erickson. I'll be giving this presentation today. I just want to start out by saying that I'm presenting this on behalf of myself and my colleague Nahal Narozi. Both of us contributed equally as primary authors to this project here. So AR collaboration has been a hot topic in augmented reality research for the past couple years because it can bring people together no matter where they're located. But these type of collaborations rely heavily on social cues, both verbal and nonverbal. The downside is that by putting on an AR headset, we're kind of limiting the amount of social cues that we can give each other because you have a big bulky headset blocking your view of your collaborators. Um, so you don't exactly know where they're looking. They could be facing you, but they might be looking at something way far off in the distance behind you. So we suggest using different eye trackers and depth sensors to regain some of these social cues. So with an AR HMD alone, we're left with just head orientation of our collaborators. We don't know exactly where they're looking, but we know a general direction that it's got to be somewhere in front of them. However, when we add on an eye tracker, it lets us get gaze direction. So we have a ray that goes from that collaborator's head out into the environment. We know that they're looking somewhere along that ray, but we don't know at which particular point along it that they're focused. Finally, if we add a depth sensor into the mix here, we can use that to calculate the termination point of that ray and figure out exactly which object that our collaborators are looking at. Unfortunately, adding these sensors adds a lot of error into the equation. We have to deal with the accuracy of both eye trackers and depth sensors, and then these gaze information can be visualized in a lot of different ways. So both of these may have significant impacts on users who are relying on this gaze information in their collaborative task. So we have some prior work in this area, and we have a preset scenario. So I'll go over kind of the scenario here. Basically, our participant comes in. He or she puts on an HMD, the HoloLens, and is able to see a crowd of 8 virtual humans pacing left and right in the area out in front of them. Next to our participant is a virtual partner who is sharing their gaze information with our participant. So that gaze is looking at one particular person out there in the crowd, but they're all moving at randomly each at different speeds. So it's difficult to tell which person it is. To make things more difficult, this gaze visualization is based on depth. So it's going to intersect the first thing along that path between the virtual partner and the object it's actually looking at. So in our graphic here, we see that our virtual partner is observing person D. However, person C has stepped between the virtual partner and person D, so it will momentarily look as though he's watching person C, even though he's not. So it does make for kind of a difficult task for our participants to try and figure out who this virtual partner is observing. So we wanted to reuse this task for 2 different scenarios, 2 different studies, so which we'll present in this work. One other quick point to bring up is that each of those people in the crowd has 3 different fixation points to simulate a more natural eye behavior from that virtual partner. So he could be looking at their head, their chest, or their waist, and he'll randomly flip between those 3 points roughly every 750 milliseconds. There's also a number that floats above that person's head that can be used by our participant to identify their selection. So they can say, oh, it's person number 1 that our partner is looking at. So for our first experiment that we present here today, we investigated 4 different independent variables, but we were mostly looking into error types and error levels and how they impact our user performance. We also investigated target depth, so we set the target to be at 2 different distances in the crowd, and we also looked at 2 different visualization methods here. So starting with our first 2 independent variables, we have that error type and error level. Error type, if we look on the left side of our screen, could be depth-based error, which means that the termination point in the forward direction would be offset So with zero amount of error, that termination point of the visualization stops right on target. However, if we apply a positive offset, it actually falls short of reaching the target. So it's hovering in space in between the virtual partner and the target. If we apply a negative error, it actually pushes that visualization too far behind the target, so it's way off in the back of the scene. Similarly, we have horizontal angular error, and another 7 different error levels for it. So at zero amount of horizontal error, that visualization is again centered right on the target, but when we add roughly 1 degree of error in any direction, it just rotates it to the left or to the right. As we apply more amounts of error there, at plus or minus 2 degrees of error, what happens is that gaze visualization runs the risk of slipping off from that target. And if that happens, if it misses the target, it will extend further back into the scene behind them. So when we reach plus or minus 3 degrees of error, that miss is actually happening consistently. So it's never actually hitting the target, it's just too far shifted to the left or to the right. Our third independent variable is the target depth. So while we do have 8 people in this crowd and they're randomly positioned in every condition, there are only 2 positions in the crowd from which our targets are selected, unbeknownst to our participants. So they can be in either position 1 or 2, as shown in the graphic here, which come out to be 3.15 meters from the partner or 5.25 meters from the partner. We have 2 different visualization methods which we investigate. The first is the truncated ray, which is a ray that starts from that partner's head and extends forward from there until it collides either with the target or collides with something between the partner and the target. So while it is hitting the target in this graphic here, the lady in the purple shirt, if this guy in the suit and the sunglasses were to take another step forward and intersect that, it would momentarily terminate on him. Similarly, we have 3D cursor. And with the 3D cursor, instead of having that directional information shown by the ray, we have a 3D object that floats at that termination point on the target or on the thing that is interrupting that gaze. So we have a couple of results to go over with you here. This is the accuracy rate of our participants for these 7 different depth errors. Along the x-axis, we have the depth offset, and for reference, we do have the participant and virtual partner shown in the bottom right to kind of give you an idea of what this gaze looked like to our participants for each of these levels. So just a reminder, at plus 105, it falls short of reaching the target, whereas at minus 105 centimeters, it extends way beyond the target. So these results are somewhat expected. We see that at these higher offsets, we have a decrease in user performance. They're making more mistakes because it's just further away from the target. As we do get closer, we see that we make less mistakes until we get to minus 70 and 35 centimeters, where they're at near 100% accuracy. Again, at 0, they're at 100% accuracy, and at minus 35 centimeters for the cursor visualization specifically, that cursor is actually shown right behind that target. So it's just right behind them. The participant has a really hard time to see that particular visualization, which is why we see that spike in accuracy rate at minus 35. We also have horizontal accuracy errors. So these are those rotations that are applied to the gaze visualization. So at 0, we see that we make a couple of mistakes for the far targets, but we're at 100% accuracy for our close targets. Interestingly, at plus or minus 1 degree of rotation applied to that visualization, we see our users are all pretty much 100% accurate. As we continue outward from there, we see these spikes in user performance. So they tend to do worse at 2 degrees of rotation, and then even worse at plus or minus 3 degrees of rotation. And this makes sense because those targets at 3 degrees of rotation often miss, the visualizations often miss that target at plus or minus 3 degrees. So the main takeaways here are that that angular error does have significant effects on our user's performance, especially when it's at levels of higher than plus or minus 1 degree. For depth error, we also see that at those at the higher levels of offset, we do have that decrease in performance, and especially when that cursor is right behind the target as well. We also ran some subjective measures which compared that truncated ray with the cursor visualization, and we found that that truncated ray visualization offered significantly higher user confidence, significantly lower cognitive load, and significantly higher usability than that cursor. And we believe that that's just because of that inclusion of that directional information. So I need to keep moving fairly quick here. The second experiment we looked into does not apply error onto these gaze visualizations. Instead, they're always right on target. We do add 2 new visualization modes into this experiment, and then we reuse those same 2 target depths that I mentioned from the first one. So on the left, we see our 2 familiar visualizations that we just saw. In the bottom right, we see a new visualization which combines the 2. So it's just the ray with that cursor added onto the termination point. In the top right, we have a new visualization called extended ray, and in this case, that ray does not depend on depth information and instead extends way past that target to a theoretical infinity, which we set to be 20 meters for the purposes of our experiment. So these show some of our results. On the left, we have response time versus these visualization modes. And what we see is that the ray and cursor visualization, the ray plus cursor visualization, offered the best performance for close targets. Truncated ray offered the best performance for far targets. Interestingly, no mistakes were made during the second study. And this was because there were no errors applied to those visualizations. Another interesting thing to note is that there was no significant effect of depth. Also, our participants had an easy time making their selections for this particular study. On the right side of the screen, we see our subjective preference for these different visualization modes. And what we noticed was that our participants significantly preferred that ray and cursor combination than they did any of the other visualization modes. And we had a similar graph for our participant confidence. So the takeaways from this are that our users significantly prefer and are significantly more confident with that ray and cursor visual combination over all of the other visualization methods. And we believe that this is because it combines that directional component with that 3D object to focus on that gives you that additional depth cue. We also saw significant differences between that truncated ray and the cursor visualization, which again we think comes down to just truncated ray having that directional component to guide our participant's eye toward the correct target. So the main takeaways from both of our studies here are that the combinations of the depth cue and the directional cue offer the best performance. They're also more preferred and offer more confidence for our users. And one more interesting takeaway is that those depth errors tend to be asymmetric. So falling short of reaching the target is actually worse for user performance than when we pass too far through the target. So thank you guys so much for listening to my talk here. I will be around in the chat to answer any questions.